main points that we had yesterday, and I've sent you already the presentation, and thank you for arranging a mailing list. We'll use this for transferring the large files that we will be sharing, and the WhatsApp group is for continuous connection with new stuff that you may see or you can share with us, with each other, because after all, it's a joint class teaching and learning experience, both for me and for you. So yesterday we touched upon basic concept in meteorology, the structure and the evolution of the atmosphere, the different layers, what was the origin of the atmosphere of our planet. We talked about two different mechanisms, one external due to the collision of comets, the other internal, probably due to volcanic activity, which is still going on. And probably those two mechanisms worked together for a very prolonged period, couple of hundreds of millions of years in the beginning of Earth history. And then life appeared on the planet by some yet to be discovered process. We have some ideas, and we will touch upon it, I think, today and tomorrow when we discuss the importance of lightning to life, to the emergence of life on planets. And then we move to some basic concepts in cloud physics, the different types of clouds, remember stratiform clouds, layer, and then cumulonimbus clouds, cumuliform clouds, two different families, different altitude, and different precipitation processes. We talked about the importance of the Clausius-Clapeyron equation to describe the saturation vapor pressure and how it is dependent on Earth's temperature, the exponential dependence. And I explained that because we are now in an era of global warming, the amount of water vapor in the air gradually increases, and so the outcome would be more strong storms and more rainy storms, a lot of rain that accumulates in the clouds. And then, after finishing this part, we moved to fundamental atmospheric electricity, and we talked about ions in the air, the different ionization processes as they are related to energy coming from the sun, galactic cosmic rays, which are modulated by the solar cycle of 11 years. And I told you about solar cycle 25, which we are now approaching solar max. It will happen in a couple of months, and you can expect some solar events which will be magnificent and hopefully not too dangerous. I touched briefly upon what is known as a black swan scenario, prolonged electrical breakdown, like with no electricity, but not just for a couple of hours, but much longer. By the way, I forgot to mention that there was such a black swan scenario, and a complete island was cut off from electricity for several months. That occurred in Zanzibar. Zanzibar, off the coast of Tanzania in Africa, is connected to the mainland with a cable. And by some accident, a boat sheared this cable. And so the entire electricity of the island was cut off for months. And it took them so long to restore it because it was very old technology, and the engineers that actually built this system were already retired, so nobody knew how to bring it back. So they had to rebuild it. And during those months in Zanzibar, several strange phenomena occurred because they did not have water, no refrigeration, so they could not store food or medicine, let alone air condition, computer communication. a lot of things happened, and there was almost a social collapse because some people had generators that could produce electricity, and they controlled water pumping, so they had the power to distribute water. And so it kind of deteriorated into sort of a criminal issue that people would sell water for really exorbitant prices. And then the UN stepped in and the government, anyway, but it showed you that civil order, the way of life we are used to, really depends on the existence of stable electrical supply. And black swan events can occur. Hopefully we will be resilient and ready. So this is about solar activity. And then we talk about other sources of ionization coming from the ground, like the emanation of radon gas, that is a radioactive gas related to the decay of radioactive isotopes, uranium and plutonium in the soil, and radium. And radon tends to be accumulated in basements and to cause maybe lung cancer if you don't ventilate the premises as you should. And then we touched upon the sick building syndrome, if you recall, and the balance between ions and aerosols in the air. We discussed the formation of particles by ions, how the ionization rate depends on altitude, and we measure it with balloons. And sometimes ions form and then change their chemical composition. They become large ions by hydration and clustering. We talked a little bit about conductivity. And then we touched upon biological effects of ions. So the sick building syndrome, the waterfall effect, the Leonard effect, and I sent you yesterday on WhatsApp the file about the importance of green and blue spaces to our health. So I hope you will have time to read it and maybe think about it, how beneficial the presence of water and of plants can be to our health, physical health. And I shared with you this, I would say, somewhat undecided findings of the relationship between ions and the mood, the emotional well-being of people. So, inconclusive evidence. Some say it does affect, but nothing quantitative had been established yet. It's an interesting field of research, but it's hard to establish because, as we said, human emotions and the general description we use to explain how we feel under certain conditions is not very mathematical, I would say. And so that paper I haven't sent you yet, I will today, surveys all the accumulated research that we have and no conclusive evidence for the beneficial impact on our spiritual and psychological state. However, for the physiological aspect, negative ions do have a good effect on the well-being of people, and it can help clean for example, the building or the environment from PM particles, particulate matter, pollution particles, and other toxins from the air. So if you use negative ionizers, that may be a good improvement to the conditions where you live. So that was yesterday. And I've sent you a slightly updated version of the program, and it's, as I said, flexible. We'll try to see how we make progress today and tomorrow. Today I'm going to talk about the global electrical circuit. I think maybe most of you learn basic uh, electrical physics in your introductory master courses, or maybe even in your bachelor degree. So you know what an electrical circuit is. You have a power supply, you have a conductor, a resistor, maybe a capacitor. Maybe you built it in your physics lab, that you have a light, you put the switch, so current flows in the circuit. And actually in this classroom we have a circuit, an electrical circuit, connected to the power supply, and there are some utilities, that the light, the projector, the air condition, the ventilator, everything is part of a circuit that is in this building and connected to the power grid outside, that is manufactured for some power stations here in Mumbai. The same concept of a large-scale global electrical circuit is employed when we discuss the atmosphere. So you'll have to stretch a little bit your imagination, because it's not something tangible that you can see. It's more of a conceptual description of the connection between electrical processes in the atmosphere, one of which, of course, is lightning, the topic of this course. And let's talk about the atmospheric electrical circuit. So in every circuit, you have to have a power supply, a battery or a generator. On Earth, if you look at the entire atmosphere between the surface and the ionosphere that we discussed yesterday, the battery, the power supply for this so-called conceptual circuit is thunderstorms, because they generate huge amounts of electricity. And we will talk about how huge they are, how much energy is produced spontaneously in the atmosphere and is being released with no interference from humans. It's just nature itself is able to produce electrical charge and then discharge it into the earth or into the atmosphere. So the battery of the electrical circuit is, of course, lightning, and lightning can be detected, as we discussed, we will discuss tomorrow, by optical, we just can see it, or by its radio emission, because lightning is a huge electrical discharge, current flowing, and when current flows, it emits radiation, electromagnetic radiation, which if we use antennas and detectors, we can actually detect and establish the direction and the range to the lightning, as we will see when we talk about lightning detection systems. So this is the battery, and where is the electricity going to? It goes to the ground, it goes up into the ionosphere, it goes into the air. Some of it is like what we call the leakage current, the presence of ions, as we discussed yesterday, and we can measure this as well using balloons and using other instruments. So the global circuit is kind of a conceptual description of all the electrical processes that take place in the air, okay? And remember, we are embedded in this electrical environment. And as we discussed yesterday, we are electrical creatures. Our brain, our nerves, everything about us relies on electricity. And so we are not, don't want to use the word immune, but we are not unaffected by the electrical conditions of the atmosphere and of the global electrical circuit. So this is a general schematic description of a circuit where the current flows. So it flows between the ionosphere, as I said, the conducting layer between 150, 300 kilometers, and the surface of the Earth. which is conducting by itself. We have the generator. This is the power supply, the lightning. And then we can, in fair weather regions where there are no thunderstorms, ions and electrons are just flowing back to the surface, and this can be measured. If I would go out with a very sensitive device into the campus, the beautiful campus, I can actually measure current flowing in the air. It's a very small electrical current. You don't feel it. Only very sensitive people may be affected by this current. It's picoampere, very small, 10 to the minus 9, but still measurable, which means that we have this kind of electrical circuit. When it's thundery and there's lightning, so we feel this part of the circuit, but normally, most of the year, it's clear. Even when it rains, not necessarily there's lightning. Suddenly, when there are clear skies, then we have what we call a fair weather part of the electrical circuit. Okay? So this concept is actually very old. It was described and conceptualized by Professor Wilson, who won the Nobel Prize in Physics back in the 1920s. By the way, maybe you paid attention, but yesterday it was announced the new Nobel Prize in Physics, and guess what? It's about electricity. Those guys worked on electrons and a very, very fast imaging of electrical processes. So we're studying together a very robust, ancient and modern field of physics. Okay? So Wilson described it in his words and published very long time ago. Some of his predictions actually were corroborated many, many years after he made them, in the 1960s, 70s, and even in the 1990s, as I will describe. But this is the concept of a global circuit, and some of the parameters that can be measured are, at every point, if I took out an instrument on the surface of the Earth, this is the voltage difference I would measure. We call it the fair weather atmospheric electric field. It's the electric field that exists between the ionosphere and the surface. It drives a current, a vertical current, towards the Earth, which is negative in polarity. The ionosphere is positive, and so the current flows downwards. And we can measure 130 volts per meter. That's what we call the fair weather electric field. And the current that flows due to this field is 2 picoamps per meter squared. So if I would have a metal plate with an area of a meter square, I would measure 2 picoamperes on that plate. So in essence, there's flowing electricity all around us, but it's very, very small and actually cannot be used. Okay? And we can actually measure the potential between the Earth and the ionosphere on such a long and vertical distance, and it's going to reach 250 kilovolts. So it's a huge potential difference between the upper ionosphere and the lower Earth, and we can calculate the resistivity of the Earth by using Ohm's law. V equals I times R, as you remember. So if you know the voltage and you know the current, you can compute the resistivity, and you see that the Earth, the air is actually very resistive. It's a very poor conductor. And this very low current that is measured everywhere is due to this very high resistivity. So the Earth, and the ionosphere are conductors, but the air is what we call is a resistor. Not very good conductor and very small current. So we can measure those parameters of the global circuit anywhere on Earth. And I have colleagues here in India that do those measurements, and I did them myself, and many of my colleagues. We actually have a global network of scientists. Each one is measuring those parameters, and we share the data. I will show you. So we measure the data in fair weather areas on the surface. We launch balloons into the air to measure the ionization rate, the conductivity, and we do measurements of thunderstorm activity. How many lightning, what is the current of the lightning, what is the polarity? Is it a negative lightning or a positive lightning? Is it coming to the ground or is it within the cloud? And I got some data for us to work on from Mumbai. I will explain tomorrow. India has a lightning detection network with many sensors around the country, and they can actually, in real time, map where lightning occurs right now. And of course, this data can be used to map the lightning distribution, to assess, for example, where are the most dangerous places in a certain area where lightning occurs. And Varsha sent us yesterday on our WhatsApp group, not sure many of you had a chance to look it up, where is the most ferocious and stormy place where you have the most concentrated lightning on Earth. It's a small lake in Venezuela, in Central America. Look it up. Really amazing spot, very small, but almost lightning every night. Okay, so I will share with you the data for the Mumbai region. I asked specifically like a rectangle around the center of the city, and I have data from 2 summers, 2022 and 2021, I believe, and we will compare, and we will have some interesting research questions that we can give our mind to it, okay? So this is about thunderstorm. And of course, there is an engineering approach to the global circuit, trying to quantify what part plays every component of the fair weather region and the stormy region, and we can mimic this circuit like this. This is what engineers like. So resistors, where the current flows, and we can do a computation of how much charge is there in the air on the surface of the Earth, how much charge is generated by lightning. And usually when I reach this part of my talk, my students usually ask me, can we use this electricity, so much energy, for free in nature? Can we harvest the energy of lightning? And my answer is that we haven't figured this out yet. If it's not done until now, probably it's a very complex issue. The main reason is that we will never know where lightning will strike. It's only a probabilistic issue, as we shall see. So, as I said, we can measure the parameters of the global circuit anywhere on Earth. Actually, you can deduce from a single measurement the parameters of the global circuit, and this has been known for a very long time, that the electric field, or sometimes you will see in the literature, it's called the potential gradient. It's the inverse, the negative sign of the electric field, that if you measure it continuously, you will see a very pronounced daily behavior. So the 130 volts per meter that I mentioned is an average value.
a daily average. But it's not constant. It changes. And people did those measurements in many, many stations, and they noticed that this electric field changes along the hours of the day and has this shape. So this is the hour of the day. This is Central Europe time, because this is in Lapland, northern Finland station. And they did those measurements in different seasons, along different hours of the day, 24 measurements per day, every hour, and they noticed that you get a minimum in the electric field, which is around 100 at 4 in the morning, and then you get a maximum of almost 260 volts per meter around 9 p.m. in the evening. So this behavior of the electric field along the hours of the day surely represents something global, because this measurement was duplicated in many, many stations around the world, and regardless where you are, you see the same pattern of the behavior of the global circuit. So minimum around 4 a.m. and then peak around 9 p.m. in the evening. Why is this happening? What is universal? What is this behavior telling us? So these are measurements that were conducted on board a ship. The ship was called the Carnegie. It was made strictly out of wood, no metal objects on the boat, because they wanted to have a very clean signal of the global circuit. They didn't want any conducting metal objects on board. I think only the compass in the captain's room was made of steel, but all the major parts of the ship were wooden. So that ship looked like, where is the image? That's the ship. I'll go back. So this is the Carnegie ship, and it sailed across the oceans and did those measurements of the electric field in many, many places around the Atlantic and the Pacific and the Indian Ocean. And everywhere they sailed, no matter where they were, they discovered the same kind of behavior of the electric field. And it was reported that there is what we call a diurnal cycle, with a minimum at 4 or 5 a.m. in the morning, universal time, and then a peak in the early evening. You can, I'm sorry, go back. So what is this? And people came up with the idea already in the 1930s that what we see as this global pattern is actually a superposition, okay, of the global lightning activity that takes place around the world, and as the Earth rotates around its axis, the lightning activity depends on solar heating and the production of clouds, and these occur everywhere depending on solar radiation. Because as we discussed yesterday in our very brief introduction to cloud physics, you have to have a rising air motion in order to cool the air and to reach saturation and produce cloud, as we discussed. And for this to occur, you have to have some warming, because as the sun warms the earth, air begins to rise, expand, adiabatically cool, and then saturate. So the production of thunderstorms actually follows solar illumination. So they usually appear after a couple of hours of solar heating in the early afternoon. And so the early afternoon in Asia and Australia precedes early afternoon in Africa and Europe. and precedes early afternoon in the US and South America and Central America. So if you look at those three plots that tell you where thunderstorms occur, what you get is what we call the Carnegie curve. It's a joint representation of Earth global electrical activity. And as I said, global lightning charges the global circuit. So this is kind of a schematic. Solar radiation produces clouds, charge is being separated in thunderstorms, generating massive currents in the form of lightning, and we see this kind of continuous charging and discharging of the global circuit occurring everywhere on the planet at different times in each continent, as I will show you. These are the parameters. Another kind of schematic. I will skip this, but it's, if you want to go deeper, it will be in the presentation that I will share with you. And so this is a superposition of everything. And as I mentioned, there is a network by the University of Reading. Yes, please. Yes, but
then still thunderstorms are happening within the clouds every now and then.
yes, correct.
That's why we are not able to see the light.
Yes. So somewhere, as I mentioned yesterday briefly, right now there are many, many thunderstorms in the Earth. Not necessarily here, but maybe in Southeast Asia, Philippines, Thailand, around there. We'll soon look at real-time data and see where lightning occurs right now. So on a global scale, there is always thunderstorms somewhere. And the global flash rate is approximately between 50 and 60 lightning strokes per second. It means that the generator, the power supply, is continuously working, okay? But the rate of discharge is not constant. This is why we have this global circuit, this behavior of the Carnegie curve that shows that there is a cycle, okay? If it was constant, like if there was a constant number of lightning every day, everywhere, then it would be a straight line. There would be no periodicity. But because the weather changes from day to day, so maybe now it's post-monsoon here in Mumbai, very little chance of thunderstorms. But elsewhere, or maybe earlier, in July and August, you would have lightning almost every day. Am I right? So every part of the Earth contributes differently to the charging of this global electrical circuit, and lightning plays this major decisive role in charging, but it's not constant at any given place. But on average, if you look at a continental scale, Asia, Africa, and America, you will get this daily behavior. So we have a network of stations that these are the names of the researchers. It's led by a lady from the University of Reading in the UK, Kerry Nicol. And these are our instruments. This is my station in the desert. This is in the UK. This is in Poland. So you can see the blue points, even in an island here in South America, Argentina, in Brazil, in India, I think it's near Calcutta. And we measure the electric field, and we are able to reproduce this daily pattern of the electric field that actually signifies the differences in lightning activity on a global scale. So this is my station. You see it's located in the southern part of Israel, which is a barren region, desert, less than 100 millimeters per year, very, very dry, very, very hot, but for some reason I like it. I like going there. It's a very quiet and desolate place, very remote. You almost see no signs of humans anywhere. So isolated and very quiet. Some people actually go there for kind of spiritual relaxation in the desert. Although the conditions are very, very hard. It gets extremely hot at day and extremely cold at night. But anyway, when I do those measurements, this is a published paper by my PhD student, we see this cycle. This is the Carnegie cycle that we are familiar with, and this is our results. We call it Ramon because it's located near a city called Mitzpe Ramon, and we see slightly different. Suddenly there is a morning peak at around 9 a.m. UT, Universal Time. Why is this sudden increase in the electrical field? We think it's because of an effect that is related to the presence of dust in the desert. In the morning hours, we have a pickup of dust by the wind, and the dust, as I mentioned, attaches to the ions in the atmosphere and increases the resistivity of the air. And if you remember Ohm's law, if you increase the resistivity, the voltage increases as well. And so we see this peak in the electric field, and then it subsides a little bit to be picked up again, not by local effects, but by the global lightning behavior around the planet. So this is how global lightning activity looks like based on, you can notice the dates are changing, based on lightning detection made by a satellite. I will run this video again. But this is, okay, so I stopped at the end of the year, and this is from an orbiting platform by a NASA satellite called Lightning Imaging Sensor, LIS. It used to be on a satellite. Now that satellite is dead, so they rebuilt it on the International Space Station. And the International Space Station rotates around the Earth 16 times per day. Okay? So each astronaut has 16 sunrises, 16 sunsets every day, which is interesting. By the way, I worked with a lot of astronauts, and one of the things that I'm always curious about is how do they sleep? Do they sleep well? Because obviously the sleep cycle, the circadian cycle, is disrupted because every 90 minutes you go from day to night again and again and again. So you and I are used to the sunset sunrise cycle, and our bodies are in tune, and it's called the circadian circuit. I'm sure you know it. So I always ask astronauts, how do you sleep? Do you sleep good? And they say that it takes a while for the body to adjust to this kind of very rapid change from day to night to day to night, and then you just put this mask on your face and you go to bed. And you sleep like an angel, they say. Okay, so what are we seeing here? First of all, I froze this moment, but observe where. Look at the map. Where? And the color is, the darker the color, the more lightning there are, okay? What can you tell from just looking at this global picture of lightning activity? Where do lightning occur mostly? Let me run this video again for you. Okay. Any comments? Where do lightning? The first and most easy and conspicuous pattern. Where lightning occurs most often? On a continental scale. It's above the three major continental areas, above the land, less than the oceans, mostly above land. South America, Africa, and Asia. Okay? So we call those areas the big chimneys. Because, you know, in a chimney you have this vertical motion of air. Warm air rises, and then goes out of the chimney to settle from other sides of the chimney. And globally, if you think of it, the tropical areas above the major continents actually take this warm and moist air, push it up, it creates massive thunderstorms. You can see the amount of lightning they produce. And then it rains out and the air falls down. Okay? And so this is December. This is winter. I'll run it again for you and maybe I'll stop. Notice how lightning migrates from winter in the northern hemisphere, which is summer in the southern hemisphere, and it moves from the southern part to the northern part. Lightning follows the summer. You know this, but this is a concrete proof. Okay? Okay, July. So in July, you obviously know this, Asia is becoming a major thunderstorm generator, and also, of course, India, Central Africa, and the Caribbean, south of the United States, Central America, and the Amazon basin, which is always pumping huge amounts of lightning. Okay? And as we progress into the what you call the dry season in winter, then lightning disappears from Asia almost entirely. It goes to Australia, Madagascar, southern parts of Africa, and of course the fierce thunderstorms about Argentina, Paraguay, and South America. So this annual cycle is showing us actually where thunderstorms occur. Okay? And my country is located here. This is the Mediterranean Sea. We are here, very small country. This is Saudi Arabia. I actually flew from Tel Aviv to Abu Dhabi, and from Abu Dhabi to Mumbai. Okay? No thunderstorms on the road. But we are unique in that we have lightning in winter above the Mediterranean Sea. Very few places in northern hemisphere winter that have lightning. It's the Mediterranean Sea, also Sea of Japan, near Japan, and Southeast Asia. Usually lightning follows summer, because summer, as we mentioned, is a solar heating maximum which drives the convective activity of the planet. Let me run this one more time for you, and you will notice that okay, so this is northern hemisphere, the end of summer, and you will see that there are places that lightning does not occur. Mostly above the oceans, very few lightning above the oceans, but also in subpolar latitudes. If we go into the North Pole region or the South Pole region, there's no lightning there. Until just the last couple of years, suddenly a new phenomena we discovered is the emergence of lightning in very northern latitudes. That never happened before. And my colleague published a paper just a week ago relating the fact that climate change actually occurs at northern and southern latitude and has this effect of removing the ice. Ice is slowly melting. And when you replace a white surface, which is reflective, has a high albedo, reflects all the sunlight back to space, you replace ice with water, which is dark. What happens is you start warming the atmosphere. And then suddenly, places that were completely devoid of lightning show new thunderstorms. So this map is not actually from the last decade. It's from 12 years ago, maybe. And now we see lightning here in northern Canada, in the Arctic region. And this is not a good sign, because it tells us that the planet is changing. Okay. And we can, of course, take those maps and do a seasonal analysis. So this is, of course, DJF, December, January, February, which is normally northern hemisphere winter. This is March, April, May, the spring. This is summer, June, July, August, and then the fall, September, October, November. And you can take a look and see this pattern that I showed you being animated and get a glimpse of the global occurrence of lightning. And you may have seen that Varsha sent us this article from the BBC. Did anybody take a look? Please do, it's on the WhatsApp. It's here, somewhere here, a small point, a lake in Venezuela that has the largest number of lightning on Earth. That's the world record. But the second most active area is the Congo Basin in Africa. No matter what season, there's always lightning there. And we do statistics. So, on average, in my country, central Israel, the Mediterranean coast, we have 25 days of lightning per year. And we measure the lightning. Actually, there's a very ancient method of measuring the occurrence of lightning. Is common to all the meteorological services in the world, and it's called a thunder day. A thunder day means a day when a thunder was heard. Even if you didn't see the lightning, if you heard the thunder, it means there was a thunderstorm. Okay, so thunder days number in my country, 25, 30 per day. In Kampala, Uganda, near the Congo Basin, the number is 240, which means 240 days of every year you have lightning. The number in Mumbai should be around 90, maybe 100. We will look at the data and you will tell me what the exact number we can figure out from the data. Okay? But definitely there are places where you get lightning in such a high frequency, and as we will see when we talk about the specific properties of the lightning discharge, that this is actually a very grave danger to be exposed to so many lightning, because lightning can kill you. And just incidentally, I was reading my morning paper, the Hindu Times, and on the first page, on the front page, it was Monday. A father and son were killed by a lightning strike not far from here. So We will talk about lightning safety and we will talk about lightning casualties. But those places where you have huge amounts of thunderstorms and people are staying outdoors, these converging factors contribute to an elevated number of casualties, as we shall see. And one of my main goals in this course for us together is to teach you in order that you will teach others about the safety of lightning. Because people don't know the basics and make stupid mistakes and get hit by thunderstorms. For example, I know that tomorrow the World Cup in cricket begins here in India. Am I right? Are you fans? You like cricket? I thought it was the national sport in India. No? I don't understand this game at all. Never understood this game. Looks so very strange to me. But I know that they are going to play in open stadiums in Hyderabad, in Delhi. I looked up the games, nothing in here, but several big stadiums. And open air stadiums during lightning season, not a good idea, especially if you play an open air sport. And I will repeat that maybe later, but the major number of casualties of outdoor sports due to lightning, can you guess which type of sport? Golf. Why golf? You're walking on a flat, almost exposed area, and you have this long metal pole that you put in the hole. Anyway, we will discuss this tomorrow. So just a thought, how safe is it to conduct the World Cup in cricket in India right now? Probably safe, but October, you still have lightning all around the country. And just last week, we had major storms in Kerala and in the eastern part, near Calcutta, all this, and the Bay of Bengal. Bay of Bengal, amazing thunderstorms. So, when we look at a lightning storm, these are just the numbers, just to get I would say a general assessment of the electrical power of a single lightning stroke. Okay? So lightning can flow to 20,000 amps of current. It's a huge amount. It's a huge amount. And it only takes 1 millisecond. Like people say, like a lightning bolt, which means very fast, but also very energetic. The total charge can be 20 coulombs. It's a huge amount of electrical charge. And the light that we see in the lightning channel, as I will explain, is caused by this very rapid heating of the air. The air is instantly heated from the ambient temperature to 30,000 degrees. That's 5 times hotter than the surface of the sun. If we look at the sun with a spectroscope and deduce the surface temperature, it's 6,000. Lightning is 30,000. And this heating leads very rapid expansion of the air, which we hear as thunder. Because when the air expands, it goes over the speed of sound, and then we hear this ba-ba-ba-ba-ba noise of the thunder. And as I will talk about after lunch break, this coincidence of light and noise in many, many cultures are considered to be the embodiment of the power of gods. In any culture, as I will review, you will hear or see stories and legends and myths about gods. Usually, God's fury and anger at humans or at the Earth that they throw lightning bolts which look like this. So, now I'm going to move from global lightning activity and the properties of lightning to the way this global activity affects us and affects all living creatures. We're going to take a break, a tea break, and then after the break I'm going to talk about the fact that when you run this huge current in the air, as I mentioned, you transmit electromagnetic energy in specific frequencies that we can monitor and detect, and some of those frequencies affect all life on this planet. And I will explain how after we take a break.